All right. Okay, so today we're going to begin chapter 8, which is conservation of linear momentum. Before I get into the chapter, I'm going to sort of give some announcements about the exam. It's going to be on Tuesday. It's going to be covering pretty much all of the material I've just covered. So think of like what was on quiz 1, what was on quiz 2. There's also a little bit of information that we haven't had a quiz for. So that was chapter 6 and 7 with work, or sorry, 5, 6, and 7. So I had just a little bit of stuff with friction, work, and this previous chapter, which was conservation of energy. So it's just a few about 2 chapters of stuff that you haven't had a quiz for. So in order to prepare for that, I'd say take a look at the homework. Otherwise, you can look at the quizzes for sort of judgment on what will be sort of asked there. The exam is going to be on Tuesday. I will not be giving a sort of half lecture on Tuesday. So it's just going to be, I'm going to, I'll put all of the stuff I say right now in an announcement in a bit. So I'm going to like start the quiz, it'll be available from, I'll say 8 in the morning until like 12 or so to, noon. So 8 to noon, that'll be the window that the test is available. And anytime within that window, you can decide to take the exam. But as soon as you start the exam, it's going to be like our quizzes. As soon as you start it, it's going to be timed. So I'm going to say like, I'll give you guys about an hour, and I'll give you like the full, what you would be getting in class. So like a full class time, hour and 15 minutes to complete your work. So there'll be like that amount of time to work on it wherever you decide to start it within that 8 to 12 time frame. However, if you do start it at 11:30, you only have 30 minutes to complete the exam, because it will automatically shut off all submissions at 12 at noon. So plan your time accordingly. There's not going to be like a normal class on Tuesday. So if you do have questions during the exam, you can email me directly. That'll be fine. I'll be checking my email. I'll still be right here. For the exam, I'll say you guys can prepare it'd be good to prepare like a page of notes. So I've gone over, what are we at already? I prepared like 57 some odd pages of notes. So I'm going to say you guys can sort of make a formula sheet on your own of things that are important, things that we've covered, things you can just have on your desk that we're not sort of like paging through. You're not going to be, I'd say you wouldn't be able to have all of your notes available, but you can have this formula sheet available. The way I'm kind of checking this is you're going to have, it's going to be kind of going through there's sort of a thing on Canvas that sort of locks your window browser and has your webcam turned on. So I'm only using this for the exams. So I'm just, because they're worth so much of your final grade, I need to have some way of controlling this. You are allowed to have, your formula sheet on your desk, but I'll be able to sort of see the video of you working on it. And I just don't want to see like ruffling through like a book or your pages or on your phone, stuff like that. Okay, so the time window, the formula sheet, it's going to be on Tuesday, 8 to 12. You have like an hour, 15 minutes to work on it. I'm not saying it's going to take the full time. I'm going to try to make it lots. I'm going to try and make it doable within the time you have. And I think that's all I have to say on it. If you guys have any questions about the exam, you could email me, or if you just have questions in general, maybe you didn't do so well on a quiz, you can always email me. Say, I've seen, the answer it's supposed to be. I still don't understand why it is, it is this way. So anytime over the weekend or even on Monday, you can email me, say, I need help with this. I'm always willing to have a session outside of class to help you guys. All right, so I'll sort of condense all that I just said into an announcement, and hopefully we all get just amazing scores on this first exam. All right, so let's start chapter 8. I don't want to get too far into chapter 8 because this is if I only cover a little bit, the next time we get back to chapter 8 material will be on Wednesday, so just under like a week from now. I don't want to get too deep. Let's go over just sort of what momentum is. So first off, we're going to specify we're looking at linear momentum. What's this? Linear momentum. What is this? Let me first write the equation. Let me first, before that, pick a color. We'll say blue. The equation for momentum is just momentum is labeled with a variable p, and that is equal to the mass of an object times the object's velocity. Momentum is a vector, so it's important which direction it's going. How can I sort of describe what momentum is? We might have heard this before. Things that are moving have momentum, or his momentum pushed him through some force or something. Well, I can sort of break down the definition as the effort needed to change an object's velocity. Okay, this might be sort of like ringing a bell from, what was it, Newton's first law, which was the law of inertia. And things with mass sort of resist moving or resist a change in movement. If they're at rest, they stay at rest. If they're in motion, they stay in motion. This is like deeply connected to an object's momentum. let me sort of, emphasize this with a little example before we get into the actual technical examples. Say we have a truck, some sort of moving truck, and a bike. These two objects are going to have a little race. These two objects are, they're not going to be going far. This is not like a cross country thing. We're going to say this is just like 10 meters or so. This is like not even the length of an average block. So, think of like your neighborhood street, half of that. So it's going to be a fairly short race. These two objects are both initially at rest. So they're going to have to change their velocity in order to try to win. The person on the bike has a very little mass compared to the person in the truck. So they have a small momentum. So we can say with a small momentum, the effort needed is small. And this logic applies to the truck. With a large momentum, there is a large effort needed to change its velocity. So they both, take off towards the finish line. Start and finish. The truck has to, we've all seen this at a stoplight. We're behind a large semi truck. It takes a while for it to get going. So you could imagine this situation. It will take a while for this to get up to speed. And then it also takes a while for it to finish, cross this finish line. Or actually what I'm going to say is it has to stop at this finish line because, I don't know, this is like a cliff or something. So we have a cliff. Now, the example, you kind of see the urgency that the truck is wanting to stop at this line. So the truck has to begin stopping a lot sooner because it has a lot of momentum. Let me try to summarize. Truck, large mass equals large effort to start and stop. So that equals a large momentum. And same logic for the bike, small mass, small effort, small momentum. The larger something's momentum, harder it is for it to stop. Or I should say, change its velocity. Small mass, small effort to start or stop. Equals small momentum. Okay. That's sort of maybe something we already know intuitively. What's the conservation of linear momentum? We're saying that momentum in a system is conserved. Well, I'm not going to do the full thing. Sort of derive things a bit more fully in the book. So if you ever have a problem with my notes, you could just check that out. how is this conserved? Well, what does the equation for momentum look like? Mass times velocity. We've seen something before that was just mass times acceleration. That was force. A force equals mass times acceleration. Well, maybe there's a relationship between those two. We'll say that, what if we take a small sliver of an object's change in momentum over time? That just means that, let's put in the equation for momentum here. And this is the equation for momentum. I can factor out the mass that's constant, at least in my problem that I've given, it's constant. And now what is this term? Change in velocity over the change in time. Or, a small sliver of velocity over a small sliver of time. That is acceleration. So that is mass times acceleration. So we can go from momentum directly into a force. This is just showing, I'll just say, so there are several other steps that the book does after this. I'm just going to jump to the point. So a force can be found with, integrating, some small slivers of how momentum may change over a small sliver of how time changes. Okay, and then from this is the part where I'm jumping to the conclusion. I'll just we'll say that if there's no external force acting on our system, so for all of our physics problems we're ever doing out in the real world, we're going to pick out what we want, and we're going to just sort of focus in on that, and we're going to call that our system. And sort of, consider everything within the system, and then look at its surroundings. So we'll say, if the sum of all external forces is 0. So I'm looking at my, precious system that I have, the truck that's moving towards the cliff or whatever I'm working on. If there's nothing, or if all the forces within this sphere that I'm looking at, if all the external forces acting on this are 0, then we can say that the momentum of the system, or the sum of all of the pieces, this is what I'm going to put right here, this is the sum of all of the small little bits. Maybe it's not just one thing that's moving. Maybe I have a system, I'm focusing in on one box coming in and colliding with another box, and I could say that whole thing before and after this sort of collision. I'm looking at a car crash, or I'm looking at whatever. I'm looking at all of the momentum. That's why I'm putting the summation of all of the little bits of my system is constant. So, all right. Let me shrink this just a hair. So we have the sum of all external forces on a system remains 0. That means the total momentum of the system remains constant. So we're going to dive into what this means in a technical example, or more thorough example coming up next. All right. So for this example, we're going to need to look at a system in two different states. Let me bring it up before I start talking about it. Example, we have an astronaut that is fixing or is replacing a broken solar panel on a space station. They decide that they don't need the old one. They decide to push the old one out into space. So they're initially holding this panel, and then they begin to, or then they give it a push out into space. What is the velocity of the astronaut after this sort of push? So I'm not going to, this is I think one problem, I'm not going to draw a picture first. I want to try to drive in what's happening. So maybe we could reason out a bit. So this astronaut, imagine him just floating in space, not connected to anything. So they're not connected to anything. They're not being affected by anything. They are at a initial velocity of 0, or they're not accelerating also. So what I'm going to start out with is kind of a, I think yesterday I sort of always started with a little checklist. This is kind of the checklist for momentum. Is I'm going to say, are there any external forces acting on this astronaut? In this situation, no, there are not. Let me finish this. So since there are no external forces, we know that the momentum of the system is constant. The momentum of the system is a constant value. So what's our system? Well, we kind of have two, this is always up to you to choose when do you want to look at maybe like an initial state and maybe after, sort of for a final state. So we first have this situation where this astronaut's holding a panel. They're holding it and they're motionless with 0 velocity. So I'm going to call that the initial state, when both objects are together and not moving. Let me first, let's go like that. So we have a momentum of the system, initial. So that's going to be our initial state. What will be our final state? Well, we're going to say after the astronaut gives this panel just a push out into space. And since we're considering both the panel and the astronaut in that system, we're going to look at both of those objects as they might move in different ways. System final. Okay. Let's sort of flesh this out. I'm going to fill in sort of the blanks. I'm going to work downward. So for the initial conditions, we have the mass of the panel times the mass, times the velocity of the panel in the initial state, plus mass of the astronaut, velocity of the astronaut in the initial state. That is equal to, and sorry, these velocities should have a vector sign. So what we're saying is the initial momentum is equal to the final momentum. Since the momentum is constant throughout, it's conserved. Mass of the panel times its velocity, final. Mass of the astronauts, the velocity of the astronaut, final. All right. Now this is where you can see that it's important to keep in mind where everything is and its velocity. Typically something's mass won't change when if I ride my bike around, I'm not losing significant amount of mass as I go. So that problem isn't, I don't have to always check to see that the mass is changing. But the velocity will be changing in most of these types of problems. So the initial state, the panel is at 0 and the astronaut is 0. They're both at rest. The astronaut's holding the panel at rest. So that means this entire left side is 0 and the right side is, I'll just go like this, the rest. Okay. Now, with just this side equal to 0, I can solve directly for what I want. What is the velocity of the astronaut? So I want to know this right here. And I'm given a mass of the astronaut, I'm given a mass of the panel, and I'm given a initial velocity of how they push this solar panel. So let's solve just the equation for this with just the variables. We have the velocity of the astronaut is equal to minus mass of the panel over mass of the astronaut times the velocity of the panel, final. All right. So we have something that's very doable here. This is where I wanted to not draw the picture first. We're going to see just from this equation, just from doing this process, we can tell how the astronaut's going to move. Okay, we have that minus, and we'll say that what was the mass of the panel was 80 kilograms over 60 kilograms. and the velocity was this right here. All right. That turns out to be, well, first, let me, this velocity needs a direction. Since I'm only given one velocity and there's no coordinate system already given with the problem, I'm just going to say that this initial velocity here, let me put this inside the parentheses. This initial velocity was just in like the X direction, I hat direction. There we go. Now I'll say is equal to minus 0.40 meters per second in the I hat direction. All right. So this velocity it's greater than the push of the panel. So the astronaut is moving faster in the opposite direction. Let's draw this picture now, and maybe this will sort of clarify. So I'm not going to draw a person on the spot. I'll just make them this sort of bean. So there's the astronaut, and they're holding solar panel. This is the initial state. And they give it a push. And I'm saying that from my problem, I'm saying that the direction of the solar panel was positive. That's usually to the right. So the solar panel moves with some velocity. To the right. And the astronaut moves in the opposite direction. I should be putting meters per second. I hat, meters per second, I hat. There we go. This is the final sort of situation. If I took two pictures of this system. So does this make sense? Well, in a previous chapter, when talking about forces, we saw that Newton's third law says that there's, for every force, there's an equal and opposite reaction. So we have a person, or this astronaut, forcing the solar panel in one direction. They're applying a force to the solar panel to get it to, get to some velocity. That also means that the same amount of force is pushing on the astronaut in the opposite direction. And since we're not on Earth, they're not having like friction with the ground to hold ourselves still. No external forces are out in space acting on this system. So we have the same amount of force. But let's look at, so a force, it does make sense, because if we have one force acting on 80 kilograms solar panel, they'll have some speed or some velocity. We have the same amount of force. We apply it to a smaller mass. We expect this mass to be faster. And that's exactly what we see with this problem. So remember to, whatever your system is when you start, You always have to look at those same exact pieces for whatever you call the final situation. You're always just taking two pictures of a system. Make sure to always include the pieces of both in each. Okay. Next up is kind of a collision problem. We'll cover collisions a bit more next week. But let me bring it up. Okay, so you are ice skating with a friend and decide to do some physics problems. You want to test out conservation of linear momentum. So you have your own mass of about 75 kilograms. And while maintaining a constant velocity going on the ice, assuming it's frictionless, you're just moving at this velocity, your friend will hand you or sort of, prop up a dumbbell for you to grab onto and pick up. So as you pass them, you then collect this mass that was at rest. So what we want to know is, what is your velocity after picking up the dumbbell? So we have this somewhat of a collision problem. So we have you. I guess the problem saying is talking to me. So there I am a square block, and I'm sliding on some ice with a constant velocity. And there's my mass. And we'll say the mass is, I'll label all of this. Actually, yeah, let me do this. We'll say it's the mass of the ice skater or skater, m sub s, the mass of the skater. This is the velocity of the skater. And we'll say this is the initial situation. And there is this smaller mass, it's the dumbbell, that's just sitting here. Mass of the dumbbell, it's just sitting there. Didn't give enough room, we'll go with that. Okay. So we have an initial condition. What's our final condition? We took the first picture. That's this. What's the final picture? Well, it's when the two are together. So after the skater has picked up the dumbbell. So we're gonna draw this picture like I'll just have the block like this. That's the skater still, and they're holding the dumbbell, and they are both moving with some velocity. All right, so that's the arrangement. That's the system. Let's consider what is in the system. Are there any external forces sort of speeding this object up, or anything slowing the skater down? I didn't write in the problem that assume ice is frictionless. We can assume it's frictionless. There's no external forces. What that means is the momentum is conserved. So the momentum of the system for the initial conditions is equal to the momentum of the system for the final condition. All right, same sort of deal. I'm just going to take this equation and write it out in full to begin with just the variables that I'm given. So we have the mass of the skater multiplied by the velocity of the skater, initial, is equal to, or sorry, adding, we're going to sum up all of the pieces of the momentum. So mass of dumbbell times the velocity of the dumbbell in its initial configuration. And we have the final case on the right hand side of the equation. All right. Here's something that we can consider just from this picture or our understanding of the problem is that, initially these two things are, separate in the initial case. But in the final case, the skater, or it says you pick up this dumbbell, and then in this final case, you're both moving with the same velocity. So we could say that's over here on the final side, we could say that the velocity of the skater is equal to the velocity of whatever the dumbbell is moving at. So we can say velocity of the skater final is equal to the velocity of the dumbbell final. And we'll just sort of label that as just velocity final without sort of a indice on it. All right. Now, let's write this out a bit more. Plus the mass of the dumbbell, the velocity of the dumbbell initially is equal to the mass of skater times final. Okay. What are some things we could break this equation down with? Well, initially, I did put specifically in this problem that the dumbbell was initially at rest. So for the initial case, the velocity of the dumbbell is 0. That makes this whole term go to 0. Okay, and since looking at the right-hand side, since the final velocity is the same in both, I could factor that out of the left and right term. So let me write this version. We're simplifying as we go. Mass of the skater plus mass of the dumbbell. Velocity final. All right. And this sort of lines up very nicely, trying to find this final velocity. I like having the term I'm solving for on the left, so I'll just flip this over. So we have mass of the skater over this sort of combination of the two. And that's all of this stuff is given already. We can find this final velocity, which is, let's put in the values, more hurt, 5 kilograms over 75 plus 10, 75 kilograms plus 10 kilograms. We initially start at 4 meters per second. We're going pretty fast. So we're just, going really fast on some ice, and we decide to pick up a dumbbell that's at rest. Our final velocity after picking the dumbbell up, still fairly fast, but it is a bit slower. Final velocity is 3.5 meters per second. All right, so we have this way of knowing that momentum is going to be conserved. We have this way of sort of finding a bit more about, this was like a collision. We could find not just like the energy that we found last chapter, we could find sort of the behavior of an object just by knowing that the momentum is going to be stored in some pieces of the problem somewhere, since we know momentum is going to be conserved. Say, well, this thing went that far at that speed, so just from looking at momentum, I know that this other piece went this way, this specific angle, with this remaining bit of momentum. So that's one way of looking at it. There's also another, in the earlier chapter, we had different set of tools looking at energy. So this is all just giving us various tools to examine a problem. For the last bit of thing I want to say today is just a little bit on kinetic energy. Since we did was just go over energy in the chapter before this. So is kinetic energy conserved in this system? From last chapter, our assumption should be yes. We have seen that momentum in the system is conserved. What about kinetic energy? I don't really need to write the equation here, but I will just to remind us. Try to make that look like a capital K is 1/2 mass times velocity squared. How does this act in, seeing if things sort of, combine together, some things maybe, moving apart? How does kinetic energy react to this situation? Let me I'll sort of in the book does some sort of derivation. I don't feel it's too enlightening. I'm just going to try to explain it in words. So we'll say earlier from conservation of energy, we said if there are no external or non-conservative forces, we said if there are no external or non-conservative forces, acting on the system, then energy is conserved. This was just sort of the conclusion from the previous chapter. A system, then energy is conserved. But I wrote that too big. We'll see. Yes. Just move this down a bit. So for momentum, now looking at momentum, we have this thing where pieces might collide, pieces might, come in from different places. We could also say the same thing. If the net external force is 0, the velocity of our system will remain constant. Therefore, the kinetic energy associated with the system does not change. Only from a factor within the system could the kinetic energy be changed in any way. And this is, the same exact sort of wrapping up point from the previous chapter. Let me I don't feel like deriving what they derive in the book. I'm going to just kind of sum it up with a picture. We have a system that is a box sliding with a velocity as a mass. If I look at everything within this system, this is my system. This is all I'm focusing on. Maybe I'll consider it being on a table or friction, but that's outside of what I'm looking at the moment. Actually, no friction in this case. So we could say there might be an external force that is, it's sitting on the table, so it will be being forced down by gravity or being held up by a table. That's the normal force. These two forces sum to 0. They cancel each other. That means it still has its mass, still has its velocity. So if the net external force is 0, velocity system remains constant. Okay. What I'm trying to say with the second sentence here is only from a factor within the system could the kinetic energy be changed in any way. So this is like one of the early problems where maybe like a spring pushes up a block and it slides up a ramp. Like that's a complicated system. And the energy isn't always going to be kinetic. It's not always going to be moving. So, that's just something that's factored into, I had like a spring and that, and it's all factored into my bubble, what I'm calling my system. I don't want to keep those in there. Just keep it like this. I'm just saying everything I'm factoring in is already in the system. If I So this is like me saying, if I have my system right here, this is my system I'm looking at, and I go outside of the system and I like push on, like my car, it's sitting out in the driveway, it's not going to affect this box sliding on this table right here. So that's a force right here, and there might be forces outside of my system, but they're not, as long as they're not affecting my system, and the sum of the forces, this is similar to the energy last time, going in is equal to going out, the sum of them are equal to 0, the velocity remains the same. So this is kind of me cheating a bit and not deriving some equations. Next time, in next class, we're going to go over some collisions. I don't want to start collisions today because next time we talk about momentum will be almost a week from now. I think people would forget by then. So I'm going to stop this coverage right here. Again, if you guys have any questions on this material or this material, let me know. But if you have questions on the exam, anything about the exam, let me know. If you have problems, you don't understand a problem or a concept, you could always let me know also. I will sort of condense what I've said earlier at the beginning of class into an announcement. And other than that, yeah, I hope you guys have a good weekend. Hope you get a lot of good studying done. I'll see you on Tuesday, or I guess I won't see you because I'm just going to release the quiz and not the quiz. I'm going to release the exam and there's not technically a class. All right. All right. So see you guys later then.